Hi there, another video where I'm going to be talking about an interesting concept in Python called duck typing. I've seen a lot of documentation and also a lot of YouTube videos and other articles on duck typing, and somehow I find there's a gap in explaining the concept to the user, and I thought maybe I will make my own version of it, so maybe hopefully you find it more interesting. This is a concept actually popularized in Python, but it's actually applicable to most dynamic object-oriented programming languages. It's applicable to Ruby, it's applicable to JavaScript and many other object-oriented languages which are dynamic in nature, right? They're dynamically typed. This word duck typing is actually based on quote by an American poet who lived till 1919. In fact, I've just listed in here. It says, "When I see a bird that walks like a duck and swims like a duck and quacks like a duck, I call that bird a duck." Well, there's a lot of history behind why he quoted that. There's a political satire, but then let me just put it across. In the real world, when you're actually trying to look at objects, many times we don't really care about what type that object belongs to. We care about the capabilities of the object. For example, let's say I just throw an object at you and I ask you to power it on. I just threw an object and asked you to power it on. Now, if you are a Java programmer, a person who comes from this type-strict, statically typed world, I have to tell you what's the type of the object. Only then you figure out where the power button is. Without knowing the type of the object, you don't even know what the object is capable of in these languages like C++, Java, C#, and so on. So if I tell you that this particular object I threw at you is a remote control, then you try to infer, oh yeah, a remote control would have a power button, and you'll search for a power button and you just click it on. Without knowing the type, you don't even try to make that inference. But in the world of duck typing, the concept is very different. When I throw an object at you and I say power it on, you don't really know, you don't really have to worry about what that object is. You just look for the power button. And you know what the power button looks like, that O and 1 surrounding that. You look for that special button and press that button on. If you don't find that button, you will throw the object back at me saying error. This does not have a power button. I don't know how to power this on. And this is the realistic example of what duck typing is. In nature, we sometimes look at the object's capabilities and utilize it rather than having to worry about the type. Another example I can tell you is a scenario where, let's say you have gone onto a beach on a vacation with a couple of tech friends, right? A very rare scenario, but imagine that if you went with some of your tech friends and onto a beach, and you're now looking at the blue sky and suddenly caught about an interesting idea, and you want to write down something, and you don't have pen and paper. So what do? You'll search around for some stick, or maybe a finger. Even a finger will do, and you start writing on sand. This is now a writable instrument. Basically, I'm using a finger like a pen, and the sand is a slate. So we are using these objects based on their capabilities. We don't really use sand and finger to demonstrate on real classrooms. We don't use it instead of a whiteboard, don't we? We don't do that, right? So we actually find out the capabilities of object and utilize it for the capabilities rather than having to worry about the type. Now, all these are the non-technical examples of duck typing that we do use in real world. Now let's get to the technical side of it. Let's say in Python, I have a small function called square. It's a very simple function I'm going to create, which is just a one-liner. So I'll say def square of n. Given an argument, it's just going to return the square of that argument. That's all it does. Very simplistic function. Now to test this function, obviously I can try square of 2, and you can see the result shows up as 4. Square is a number, right? So when I say square of 2, n is equal to 2, and n into n, that's 2 into 2 is what is returned, and you get 4 here. But try square of 3. It works. What about trying to give a floating point? 3.6. It still works. Closely observe, the square function has no information about the type of argument expected. Nowhere in the square function I mentioned that I need a number, I need a float, I need an integer. No. Just give me n, I'll just multiply n with n and return the result. So some of you might ask, what happens if I say square of hello? And this is where it fails. You get this type error with all the trace back in here, which shows that square of hello return n into n can't multiply sequence of non-int of type string. This function does not do any kind of type checking. Pass it any argument, it's just going to multiply the argument in itself. And obviously you cannot multiply a string with a string, and that's why you got this error. Now let us say I want to use this function to square not just one particular value, but a list of values and return a result. One of the ways you will do that using built-in strategies in Python. One, you can use comprehension, or the other one, you can use the map function, right? Both will work likewise. So if I try to say map of square, and let's assume that I have values first. I'll just say values is equal to a list of some random numbers in here. Maybe it's got integer, floating point, numbers. Now all I could do is I could say map square and values. Unfortunately, map is optimized, I would say, in modern Python. It does not actually do the computation when you call it. It just returns an iterable object. So you need to iterate over this map object, only then the actual computation happens. It's also called as a lazy mapper, right? That's how it is in Python 3. So what I can do is I can actually try to construct a list from it. You can always create a list from any iterable object. So I'm going to use that principle. I'm just going to say list of map of square comma values, and now we can see it actually computes all the result. 4 becomes 16, 5 becomes 25, 8 becomes 64, 2 becomes 4. So it goes on likewise for every number. That's why it's called as a map, like a set theory thing, right? Input set is mapped with a function to output set. That's what you see it. This is one-to-one mapping that you see here. So this input becomes so-and-so output based on the function being applied. This is also called as a higher order function, because you see a function that takes another function as an argument and performs some activity here. Now this map function, which is built into Python, is very simplistic. It just does exactly what is intended to, right? Just call that function every single entity of values. But if values had a string in here, like say A, it's just going to payload with an error. But maybe what I want is, if at all I have some non-compatible data in here, I just want to ignore it. Maybe what I want to do is in the output, I want to substitute them with none or 0 or any default value of my choice. So how do I do that? In order to perform that, I have to create my own version of map, which takes care of this activity. So what I'll do now is I'm just going to create another cell, and here I'm going to create my own function. I'm going to call this apply map, which does a similar thing like what the map function does, that it's going to create a list directly. The apply map is going to take a function as one of the argument and the data set as another argument. I'm just going to call it data, and the result is going to be a list. Let's start with an empty list. So what needs to be done is you need to iterate over each item of data. So I'm just going to type for v in data for each element in data. So when you try to iterate, let's assume I'm going to pass values as this particular parameter, right? So what it's going to do, first time it's going to just iterate over 4. V will be equal to 4. Then it has to call this function on V. Some of you might ask, why not put square function here? I want to make this more generic. Maybe you want to square numbers, you want to cube numbers, you want to do anything. You want to keep the actual operation I want to perform as a separate entity that I can pass dynamically, right? That's the true essence of higher order functions. So here I say for v in data, I'm just going to type result is equal to r is equal to fn of v. Call the function passes an argument with v as a parameter, and whatever the outcome is, append it to the final result. I'm just going to say result dot append of r, and then return result. Now for now, assuming that the values do not have any of these miscreant data, for all numbers, going to work just like the map function, list of map function. So it's going to work similar to that. So we just type apply map of square. That's the first argument, which function to be called, and what data set, which is values. You can see it works just like the built-in map function. So what exactly happens is that square is passed as a first argument. So function is passed as an argument here. So this function is getting invoked. Whenever you see fn being invoked, technically it's calling square function, passing first 4 as an argument. So whatever outcome is appended to the result. That becomes 16. Next time 5 becomes 25, appended to the result. It goes on, and ultimately the result is given to us. So you get a one-to-one mapping here. 4 becomes 16, 5 becomes 25, 8 becomes 64, and so on. Now, obviously, if at all I have an argument that's not really going to be compatible with square function, this also is going to fail exactly like the original map function. You get the same error like we saw before. In the earlier cell, even the built-in map function failed the same way, right? Same way. Now, what I want to do is that I want to add some intelligence in here. The first step I'm going to do is I'm going to use this approach called look before you leap. I'll tell you what that means. So I'm going to check if the value, right? I'm going to say type of value in, if it's an integer or a float, then you compute the result. I told you this approach where you're going to take a precautionary check. You want to check whether this type of this argument is really compatible with this function, right? So it's going to be compatible only if it's an integer or floating point, basically numbers. So I can actually, this is called as a look before you leap approach, also called as LBYL, right? Look before you leap approach. All of these are not duck typing. Just telling you, I'm just going to need to duck typing in a while, because first you need to understand what are the traditional approaches of problem solving that you'll do and how duck typing improvises, right? I'm going to show you that step by step. So here what I'll do is I'll just check if it's compatible, compute it. If it's not compatible, I'll say R is equal to, what I'm going to do is I'm going to use something called default, and default is going to be another parameter which I'll take, making it very generic. Default is none, default argument. And now when I try to run this, it's going to work just that. For the value A, the result is none. You don't want it to be none. You want to store 0. You have an option where you can just pass third argument as 0. What you want to store as default argument for non-compatible value in values, right? So you use this technique. This works perfectly, right? But there's a problem with this. It's not really scalable. I'll tell you why it's not scalable. Right now, I'm explicitly checking for the type of value to be an integer or a floating point. But you know what? There are many other types of numbers. Python also has a complex number. It's a built-in data type. So if I try to put a complex number in here, let's say I'm going to put the last number as complex number. I'll say 4 plus 5j. You can see that you can actually square complex numbers, but here, because I'm specifically checking for integer or floating point and not complex number, this won't work. Which means that this function should take care of all kinds of numerical types. And that's not going to scale. I'll tell you why. Because tomorrow if I invent my own numerical type, new type of number, call it whole number, or maybe I can call it positive integer, or I can call it rational, fraction, decimal, whatever. So I need to modify this function to handle those types. So is there a better solution than this? Yes, there is. And that is the traditional approach used in many other object-oriented programming languages. We call this as generalization approach, which I'm going to show you now, which also follows the same look before you leap, but using generalization. What is generalization? Well, this is also sometimes referred to as Liskov's substitution principle. Generalization using Liskov substitution principle. What is this all about? If you ever have encountered statically typed languages like Java or C++ or even C#, one thing that you'll normally observe, especially when dealing with certain data structures like collections and all that, you'll find a deep down inheritance hierarchy, right? You'll find an abstract base class, some more subclasses of the abstract base class. It goes on all the way down till you have the actual concrete implementation. And you'll also find interfaces. In language like Java, interfaces are very commonly found. So these actually define the contracts that can be applied for an object. They typify an object, and this object is should be capable of so and so features. So you need to have abstract base classes to actually make things work here. That means there's a lot of design level complexity involved, right? But that's being done by the language creators or the library creators, and we users try to use it. Now, how does it work in this case? Python did introduce support for abstract based classes to support generalization, just like other mainstream statically typed languages. It's available as an option since Python 3.5. The community is sort of divided. Say the new age community folks of Python really embrace this feature because they might be coming from language like Java and say like, oh, I like this feature in Java, this is there in Python, and I really like it. And there are old timers, people like me, who say, this just added noise. Okay, it's all debated. So I'm not going to say this is good or this bad. It's just up to you to make up your decision, right? So here's what you do with generalization. All you do is inside this function, I'm just going to say from numbers, import number. Okay, some of you might raise a red flag right here. How do you put an import inside a function? I believe in local imports. Okay, I'm opinionated there. So yeah, if you don't want to do local imports, you want to put it on top, you can do it and put it on top, no problem. It's up to you. I like to keep things more cleanly organized. I don't like to clutter the global namespace. I like to keep this module is going to be used only inside this function in this scope. It's not going to be used anywhere else. That's the reason I put this inside the function. Perfectly okay to do that. Nothing wrong at all. Okay, contrary to what people might tell you. So there's not some kind of a declaratives that you put in the beginning. It can be anywhere that you want, where it makes sense. So because I feel this class called number is only going to be used inside apply map and nowhere outside, there's a point of importing outside in this case, right? So here is the result is equal to empty list. And what I'm going to do here is, this is what I'm going to change. Instead of using type of v in specific types, I'm going to say if is instance of v number. I'll tell you what the is instance built-in function does in Python. It's very similar to the instance of operators that you'll find in many other languages, or instance of macros or operators. What it means is that it checks whether a given object is an instance of a class that you pass as a second argument or any of its subclasses. It's like a link. I can ask you, what car do you own? Now you might find it offending and say, no, I don't own a car, I own a truck. Or you might say, I own a bike. How do I put the point across? How do I ask you generically? I say, which vehicle do you own? And when I say vehicle is the base class for truck, car, SUV, bike, you name it, bicycle, you name it, even a ship or even a yacht, anything. So it's just the same way here. So the is instance is going to check whether a given argument which you pass as first parameter is an instance of this particular class or any of its subclass. Is it a kind of number? That's it. Very generic. This is also called as generalization. This is what is Liskov's substitution principle. In many other languages, I'm going to type it off below just to give you an insight. If you did work on languages like Java or C++, you would have this kind of notation and say, person P is equal to new employee. You do this, right? I mean, this is like Java syntax, okay? So basically what I'm trying to say is that the variable P is of type person, but it actually represents an instance of employee, a different class, right? Well, basically this would work assuming that the employee class is a subclass of person. A subclass of person. That's what we call as Liskov substitution principle. So if all I got an employee object, I can check whether it's an instance of person class. It will be an instance of person. An employee is a person, right? So it's the same analogy being used here in the Python world, just that we don't have static declarations, just that you can use the instance of to check whether an object is an instance of this number. And this works. This perfectly works. This also is look before you leap approach, but just using generalization in here, using Liskov substitution principle. Same thing. You just say check if the number is values an instance of number, call the function, otherwise use the defaults. Works. And you can see that last time when I tried out with complex number, the complex number 4 plus 5j was reported as 0 because I did not specifically check for complex number here. Here there are no specific checks for integer or float or complex. Any number will do. Therefore, even complex number works. You can try with even fraction. Fraction is actually available as a module. So if at all I try to use, I'll just do one thing. I'll just say from fractions import fraction. I hope it's fractions. I might be wrong. Just verify that. Yeah, it's correct. Yeah. And then I also had a fraction number here. Fraction of 1 by 2. It'll work. because this fraction class also inherits number. It's being designed that way. So you can see it shows by 4. So this is the approach that is very commonly used in languages like Java, C++, C#, and so on. Very common. And now Python does support it if you really want to use this feature. Now, what is duck typing? Duck typing is even more pragmatic, practical, super simplified. Now, I'll show you the problem with this design though, okay? This generalization as such. Now, this particular function, apply map, is not a truly generic function. When you create a higher order function, you want to make sure the function is as generic as possible, which is unfortunately not the case in here. I'll tell you the reason why. Okay, I'm just going to remove all this fraction stuff for now, just as a demonstration. I'll just copy this code. Let's assume that I'm not going to deal with values which are numbers this time. Let me just use something called users this time. Okay, users is equal to John, Jane, Emily, Smith. Sure. I just use some random names in here. Obviously, I can't square them. What I want to do is I want to convert all of them to uppercase. So I'm going to create another function. Some of you might now looking at it and say, why aren't you using a lambda expression? Yes, ideally you should be using lambda expressions for simple use case like this. I don't want to crowd too much of topics in a short video like this. So that's the reason I'm keeping things simple. Let me not talk about lambda expressions at this point, right? But that's what you should be doing in reality. I'm going to keep it very simple though. Let's say toUpper of u, return u.upper. Give me an argument. I'll call .upper method on it. Return. Obviously, it works only for strings, right? String compatible data. So if all I try to use apply map on this one, when I say apply map of toUpper and users, you know what happens. Didn't work, right? Because this apply map somehow is still hard-coded to work with only numbers. It expects argument to be numbers here. So it's not a really generic algorithm. So I'm going to show you how I'm going to approach the same solution using duck typing. So I'll do this time. I'll take this version, right? I'll just copy this version. Where I use generalization first. I'm going to use duck typing this time. I'm going to paste it here. It's not generalization now. It's going to be using duck typing. When it comes to duck typing, you don't use the paradigm called look before you leap. But there's another paradigm. It's called it's easy to ask for forgiveness than permission. Wow, long sentence. Basically what this means is it's called EAFP approach. Well, all these approaches and paradigms are very similar to definitely you would have heard about VCVig. What you see is what you get. DWIM, do what I mean. Similarly, these are the kind of paradigms, right? So it's easy to ask for forgiveness than permission. What do you mean by that? You don't really check for the type of argument anymore. Forget about this. You don't need this line, right? Because I'm not going to be checking for types at all anywhere. What I do instead is I'm going to replace this with try. Try calling the function with a value. If it raises an exception, ask for forgiveness. If it raises an exception, ask for forgiveness. Oh, let it be the default. That's it. Very simple. So you just try running this time. It works. You can try to see. When I try to put a here, it substituted with 0. What exactly happened was this. The function was called with the value being passed anyways. The function did not raise an exception. Maybe the function worked without a problem. You get the result and you append that result in here. But if this particular function had raised an exception, obviously it would have gone to the except clause where I'm just going to make r equal to whatever default argument that is being passed here, which is 0. Well, one of the things that you see here is that absolutely no information about type. I'm not really looking for what type of argument is being passed, right? So that's what I mean by telling if it walks like a duck, swims like a duck, quacks like a duck, it's a duck. You don't really ask for a type. You just look at the characteristics and you decide on that. Any value that can be multiplied with itself, I believe it's a number. So it's assuming it's a number and it's going to work, right? So the beauty of this particular design is that it's going to work very generically. For example, if I try the same thing with the other variant, right? We just copy this code so far here. And remember the other example I showed you where I used just toUpper and users, right? To code. I'm going to put that instead in here. Instead of numbers, this time you have a function called toUpper of u, which will return u.upper, and users is a list of strings. Now what I'm going to do is the same apply map function with no change in it. Absolutely no change, right? I'm just going to change this to toUpper and users. Maybe I want to have the default as empty string, but incompatible data. Works. So if you put some numbers in here, like say if I just sprinkle some numbers in here, 34, let's try a floating point, 4.5. I could also add some things like Boolean values, like say true. All the non-compatible types do not have an upper method. So when you try to say v.upper is going to raise an exception, because raise an exception, you just assume R is default, it's going to work. This is the true essence of duck typing. The whole idea of duck typing is, in a way, I could say that duck typing is kind of anti-type checking, right? You don't really worry about the type, you worry about the characteristics of an object. I would say in my words, duck typing is more like this. So what duck typing really means is, I don't care who you are. I care about what you can do. So duck typing is all about, you don't really care about who the object is, what type it belongs to, right? You don't worry about the type, but you care about, can this object perform this activity? There's a lot of practical examples like these. What I showed you is a very simplistic example. In real world, I can think of one more use case. For example, there are certain frameworks or certain functions which will take an argument. One of the things I can think of is the XML library, LXML. LXML is a classic example, or even elementary library. So there's a parse function in LXML or elementary compliant libraries, right? So this parse function, you would expect to pass a file object, but it need not have to be a file object. It can be any object that has read method. You just pass an object that has read method, it's going to work with it. So it can be even not just a open file object. It can be a HTTP response object. HTTP response object has read method, so obviously you can also pass it. It'll work, assuming that it generates HTML, XML. You can parse it. So types are not really checked there. They only care about the capabilities. They check whether this method is available. They just invoke the method, and they put this in a try except block. If the method invocation fails, you know that that particular object that you passed as an argument is not compatible, and you just tail out. And this actually makes object-oriented design very pragmatic, very approachable. In a way, the reason I really like Python and even Ruby to that extent is that they don't clutter us with too much of inheritance hierarchies. If you ever observed in Python in the early days, at least before Python 3.5, that is, you never see some kind of inheritance hierarchy with all these collections. You don't see that tuple, list and all fall in some kind of a collections category with some abstract based classes representing them. But these were introduced in 3.5 to appease, or say rather please, the people who come from statically typed background, who want to carry forward that learning that they have from the statically typed background and want to use them in Python. And that's what it is all about. But the traditional approach of practical object orientation is duck typing, and this is what it is, right? I hope you found this concept useful. I hope you found this video useful. If you do have any confusion, or if you didn't understand any of these concepts I told you, please do comment so I can actually make more elaborate videos on the same regard. Hope you found this video useful. Thank you very much. Hope to meet you in another one.